So what was the analogy that they used in that presentation for electrons being excited and de-excited? The metaphor, maybe. How did they explain that in that video? So they talked about steps. What was somebody else? What was the aspect of the steps, and how did it relate to electrons and their energy? Jumping around the nucleus? Okay. Listening to the lights hum. Okay, so you have an electron. They made the analogy that the bottom of the staircase was the nucleus, that electrons move relative to the nucleus by going up the staircase. Okay? That in order to take a step, you needed to have a specific amount of energy. You had to have exactly the right amount of energy. If you think about it, kind of like lifting your foot, you know? You're walking up a staircase. What happens other than falling down? What happens if you don't lift your foot high enough to go to the next step? You can't go forward anymore, right? You're stuck. You have to have enough energy. And if you think about it as lifting your foot, you've got to lift your foot high enough to actually get on the next step before you can step onto that step. So electrons have a certain amount of energy. In order for them to go to a more distant orbit, is a way of thinking of it. Again, in our minds, we're probably thinking Bohr. We're gonna translate that over to quantum mechanical model in just a moment. But from the Bohr model, each ring is energy. The farther you get away from the nucleus, the more energy that's required to be in that state. An electron that's in an orbit that's far from the nucleus requires a lot more energy to be there than an electron that's close. And that movement between the different orbitals, thank you, Ike, that the energy that's required for you to move, again, we're assuming that there's a space for that electron to be, because all of the orbitals have a maximum amount of electrons, right? So you're assuming that you're moving into an orbital that has room for that electron. And so adding energy to it means that that electron is going to try to move away from the nucleus as energy is added, and each step represents another energy level that they've moved away. Now, one of the principles of matter that we need to remember all the time is that matter likes to be in its ground state, or its least active state. That's really distracting. I apologize for that. He's an athletic director. What does he know? Sports people. I'm joking, of course. I played center and middle linebacker and wrestled and all that stuff too. So I'm a jock geek hybrid thing. The only thing I wasn't, I was in the band, I was in the dramas, I was in music, what didn't I do? I didn't really have a life. I was too busy doing a life. Hey, I did have a life. Anyway, so these steps of the ladder moving from the nucleus out, it takes energy to get there, but this is one of those things we talked about before where we kind of we kind of personalize things. I said before that, or I'll say right now, that these electrons, they don't want to work. They want to be at the least amount of activity possible. They're kind of like, well, I'll let you come up with your own analogies. You're going to do as little work as possible. You're going to do just enough to get by. You want to get there as quickly as possible. So that's what electrons want to do. You give them energy and they take the steps up, but you know what? Their inclination is to want to be back at back as low as they can go. And so if you think about the electron as getting energy and going up these steps, it's absorbing energy to go up the steps, which means going to an orbit that's farther away from the nucleus, but its desire is to be as lazy as possible. So as quickly as it can, it's going to regress back down to the lowest state it can possibly be at. So notice on the video too, they reminded us that it takes a certain amount of energy to get up there. In order for it to recede back down to a lower energy level, it has to give off energy. It can't destroy energy. It has to give it off. It has to transfer it. And the way it does that is by emitting light. Okay, by emitting light. Now, if you take into that also where he said that each individual atom has its own unique staircase. In other words, there's different steps between each orbital, between each energy level as it goes up. That means for every energy level that the electron comes down when it emits that light, it emits light at the same energy or the same frequency as would have been required for it to go up. And so every step down means that as the electron makes that step down, it emits light. And emits light in a frequency to the energy that it gave off to get to the next step down. So you're giving the electron energy to have it step up, but then as soon as it can, as soon as the teacher's back is turned, it's going to try to go back to sleep. And boom, it's going to start moving back down and emitting light. Now that would be helpful for me because, as I see the eyes shifting and closing, if I turned around and suddenly there flashes a light on the board, I would know what I already know. Something's happening behind me where the energy level is suddenly falling down. I have to do something to re-excite the class, to re-energize the class, to try to move you back up to a higher energy level so that we have more activity, more learning taking place. But, at some point, you fall into the nucleus, you get that black hole, you're gone, and then there's nothing more I can do. Anyway, that analogy dies. We're going to take this information now with the light. Hopefully, again, Crash Course, I think they do a good job. I've not watched very many with the astronomy teacher before. I usually see the brothers. But take that information. We're going to go back over some of what we did yesterday because this information is fundamentally important. You need to understand these quantum mechanical orbits. It's very important to the rest of what we do here in chemistry. And so I'm going to backtrack a little bit. Yesterday I told some people I was a little bit off game yesterday. So I'm going to approach some of this again. If you have notes, just go over the notes of some of the things we've already covered, and then we'll build on those and do what we can, because we are taking the rest of this week to cover probably like 8 pages in the text. The chapter ends at 125. We're on 113. We've got 12 pages and 4 days to do it. Okay? So the reason I left this much time doesn't mean we're going to necessarily take all that time. If you're all bored, you've got it down by Friday, we'll move on. But I want to give us enough time to make sure that we really understand this as best we can. And part of this as well is, you've seen that you need to teach this material several different ways, and each way you do it, you're building more information so that the next time you review it, it makes more sense. There's one way of building the electron configuration that uses a slant diagram, and there's one way that teaches it using the periodic table. I'm going to teach both of those ways, and then hopefully between one will help you understand the other, and then ultimately they'll cooperate together to help you understand more fully what I mean when I say, let's build an electron configuration. Okay. So going back to the Bohr model, again, a lot of stuff that was just on the video, but there's a nucleus with the positive and the neutral particles. I'm starting on about, like I said, 1/12, and that figure 312 is kind of what I'm looking at now for my talking points. But in the Bohr model of the atom, there's a nucleus with positive and neutral particles, and there are electrons that are orbiting around the nucleus. For now, we're going to keep our discussion into a solar kind of an orbit. They're just flat racetracks. And those stair steps, if you think about that, represent each stair step is another orbit out from the center. Now, in the quantum mechanical model, we know that's not actually, or that's currently not the theory of how this works. But it helps us understand these basic principles. So we're going to continue to go with this for now. We talked about electrons being excited. When an electron is excited, means it's received new energy. You're in class and suddenly Mr. Patty says something loud, and he says it in a way so that it gets your attention, like, what was that? And you think he's crazy, but what he's actually trying to do is excite you and re-engage you into the class, right? So there's that energy level that goes up when an electron is excited. So if I say to you, what does it mean when an electron is excited? It means that it has received energy, and the consequence of that, it may have moved up to a higher energy level. It may have moved to a different orbit. Now, when that electron then collapses back because they are by nature lazy and want to do as little as possible to get by, they fall back to the center. That's called de-excitement, or it's de-excited. And when that happens, because it's losing energy, energy can't be lost. It has to be given. It has to be transmitted or transferred. It does that by releasing energy in the form of light. Now, part of what Bohr in his model said, and again, I'm just going to draw a simple circle that represents the entire nucleus. That's going to be all neutrons and protons right there. That around the nucleus, there were different energy levels, and they were discrete energy levels. Again, this is the stair-step idea. The electron can either be in this orbit, or it can be in this orbit. It cannot be somewhere in between and exist for long periods of time. And that's why we said yesterday about quantum. There used to be a series on TV called Quantum Leap. Scott Bakula was in that before he was, captain of the Enterprise in the series, the most recent series, the series that has it closest to our time, But anyway, he had this principle of existence in Quantum Leap, saying that he could move from one place to another because there were discrete time periods, there were discrete events in history. The idea here of quantum is that an electron can exist here, and it can exist here. It can orbit, let's say, in this orbital or exist in this orbital, but it cannot exist in a middle orbital. Now, the interesting thing about this, and I alluded to it, this is kind of outside the text, I think, but not only can an electron only orbit here and only orbit here, but it can only exist here and exist here. And one of the phenomenons in physics is that electrons that are in this orbital are here, and then they are instantaneously here. And it appears, to the best of our ability to understand, that they do not exist between here and here. That the electrons actually cease to exist and then re-exist when they reach the appropriate energy level. So one way of thinking about that might be that it happens so incredibly quickly that it's beyond our ability to perceive, or there's something else going on here about what it means to be. And that gets in the whole realm of philosophy, right? Does the electron cease to exist, or does it still exist just beyond our ability to understand how and where it exists? But that's the whole idea of quantum. It's one place or it's the other place, but it not only doesn't orbit in between, it doesn't exist in between, which is kind of cool to think about, right? Yes? I think it's cool to think about. Like, kind of things like you sit here and think that this class is 50 minutes long, but how do we know it's not 1,000 years long? And we have these big gaps in between where we're all simultaneously frozen. Stuff like that. It appears to us to be 50 minutes long, so we'll go with that. So the different levels of energy, excitement moves them out, they gain energy. When they move back in, they fall back in, they are de-excited, they release energy, and that energy is released in the form of light. I mentioned too that Bohr's mathematical model, the math he used to prove this, he did it all with paper and pencil, a legal pad, did the math to show it worked, then went to the lab and proved his math by doing the experiments, and the math is so spot on that his math is still taught for college chemistry classes to explain the movements of the electron. Now, one of the principles of quantum mechanics is that they noted that you can never identify a electron's position and its momentum at the same time. It's mass that has motion, so it has momentum, and its location, and that's why quantum mechanics kind of moves into this idea of, rather than discrete orbitals, that the orbitals now are orbital clouds. Again, I'm getting slightly ahead of our notes. The quantum mechanical model on page 114 is where we pick this up, and it gives you a few distinctions between the Bohr model and the quantum mechanical model. The first one was about the types of orbitals. Representing orbitals like this, I sometimes want to say it looks like a record player with all the different grooves, but many of you don't even know what a record is. So, a center with orbits that go around the outside of it. Maybe if you've ever looked at the back of a CD or something, you see the little grooves and things like that. You can think about the orbits like that. But again, a record or a CD is a two-dimensional object. Atoms actually exist in 3 dimensions. And so we started talking yesterday about the different orbital shapes in a quantum mechanical model. Now, one thing about all these different shapes, these are called orbitals, and I don't think I stressed this yesterday, but an orbital doesn't represent the track of the electron. Okay? He's back. It doesn't represent the track. In other words, yesterday when I drew the s orbital, and I said s orbitals are spheres. Kind of give the idea of 3 dimensions, that the s orbital is a sphere. If you looked at the Bohr model, you would say, okay, the electrons exist on this track, or in this track, or in the next track. They have a very specific course that they run. When I draw an orbital like the s orbital here, what I'm telling you is that the electron exists due to its probability inside of this circle. Does it absolutely always exist within this sphere? No, but the probability is incredibly high that it's going to be inside of the sphere. As a matter of fact, there's not necessarily a greater probability that it's going to be on the very edge of the sphere. It's not just running on the skin of the volleyball or beach ball or whatever you visualize it as. It's not just on the outside, very most outside edge. It's actually exists somewhere within that entire domain, the entire region that is the skin and the interior of the ball. So in the book, they give the analogy of the dog. They say in this Bohr model, if you think about a dog being chained up in your backyard, if I were to put a stake in the middle of my backyard here, and by stake I mean like the thing you drive through Dracula, not the thing you eat at table, okay? You put a stake in the middle of the yard, and you chain up your dog to that. Well, if you chain a dog to that, you would know that over here, the dog could be anywhere between the stake and the limit of its chain. It could be anywhere. You know, if you're breaking into your neighbor's yard because they, you know, you think they have something of yours, and so you're going to check it out, you jump the fence, there's a dog out there, you know that if I'm anywhere within the circle that chain lets that dog be, they can get me, right? The dog can move back and forth inside that, so anywhere in there is a possible place that dog could be. How do you take that information and that kind of thinking over to the Bohr model? Well, this one says, and in the book it talked about this, that let's say that the dog is, rather than on a chain, and this isn't exactly what the book says, but this might work better, rather than a chain, on this kind of a model, the dog is actually hooked to a pipe. The pipe that sets its course. In other words, the dog, if the dog has a pivoted pipe right here, and the dog is right there, that's exactly where the dog has to be. The dog can't be any farther away than the pipe, it can't be any closer than the pipe, it's going to be right there. And so when you're in the backyard, you say, okay, where can the dog get me? Well, it's only going to get you if you happen to be right on that mark right there. If you are anywhere else, like if you're inside the pipe or outside the pipe, the dog can't reach you there. Or maybe it's Kentucky, right? You know, horses, when they walk the horses, they have them on a center pivot pole. I don't even know what that's called. But they walk in circles and they tread the ground. And they're always at a very specific distance from the pivot. Always. And they just, you know, expend a lot of energy but do no work because they keep going around and around the same place. That's this kind of a Bohr model. Our understanding of the model now is quantum mechanical, which is as if that horse had a rope rather than a pole. And it can be anywhere inside that shape. Matter of fact, it can be outside the shape, but due to statistics, probability, the greatest probability is going to be inside that shape. And that's how we understand where the electrons can be. So we did three different shapes, or three different orbitals yesterday. We described two of the shapes because the two shapes that we can even attempt to draw, the first two are the easiest ones. The third one, the d orbital, is too complicated for us to try to draw without using computer-aided design to draw that orbital. But the vast majority of all the elements we're going to look at have electrons that are only in the s, the p, and the d orbitals. There is an f orbital, but it gets even crazier from there. Because let's look over here. We've got the d block. We said there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A position to hold 10 different electrons. We said there are 5 orbitals, 5 d orbitals per energy level with 2 electrons per orbital. Down here, this is the f block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Holds 14 electrons. It has 7 orbitals, each holding 2 electrons to form the entire block. Okay? You think my little 3-dimensional propeller is hard to understand? What about 5 and then 7? It just gets too hard to draw on the board. So we're not even going to go there. Just know that you can look up those shapes if you care. The most significant thing for you to remember is that the electrons fill energy levels, that electrons are like your classmates. They're lazy and they want to do as little as possible, and they're going to fill in a specific order, and they're going to fill from bottom to top. If you think of the staircase, they're going to fill from the first step to the last step in order. Nobody's going to choose to sit with a gap between them, because if they find a gap between them, they're going to say, hey, I can slack off. he'll do my homework for me. I'll just fall at the next energy level, emit some light, and then fill in. So they all fill in to the middle naturally, unless they receive energy from the outside, which excites them, moves them out, but then as quickly as they can, they fall back in and emit light and go back to the ground state, the normal natural state. And the only thing that keeps them all from collapsing to the middle and everybody living in the 1s orbital is each orbital can only hold 2 electrons. Again, the details of why that is beyond the scope of this course. We're just going to accept that it is. So on 117, we actually get into building, and this is where we kind of left off yesterday, about actually building the electron configurations for the individual atoms. And as I said, there's 2 different ways to look at this. One is using the periodic table, which we started yesterday. Today, I'm going to go through and draw a slant table or a slant diagram. This is the way that I learned it back in high school, all those many, many years ago. Wow. It was a while ago. I just started thinking about the years. It was probably like 36 years ago. So the old-fashioned way of doing it, just after dinosaurs died off, you know. We talked about the different energy levels, and the energy levels over here correspond to the rows, the first row, second row, third row, and so on. Okay, we're going to refer to those as the different energy levels. Within each energy level, there are multiple orbitals. So each energy level has multiple orbitals, and when we do the electron configurations, we're going to start with, first of all, the energy level. Think of the energy level as the basic, maybe if we continue to use that stair-step analogy, the energy level is a set of stairs. Let's say each set of stairs. I mean, like you got a staircase, there's maybe a section where here's a set of stairs together, and there's another set of stairs together. Matter of fact, if you do remember that staircase, it kind of looked like this, the way they portrayed it, that there was step, step, big step, little step, bigger step, big step. Think about each one of these major steps as an energy level. We're taking it to the next level, okay? But once you get to the next level, there may be smaller incremental steps that go to the different orbitals, the s orbitals, the p orbitals, and the d orbitals. To go to the next energy level is another large step that requires you to get there before you can start filling additional orbitals. So each energy level has different orbitals within it. And we said that the first energy level, that's going to be for hydrogen and helium in their natural states, the first orbital, or the first energy level, only has an s orbital. It has a single s orbital, and that single s orbital can hold 2 electrons, right? So in the first energy level, s orbital can hold 2 electrons. The second energy level can hold its first orbital, and the second energy level is also an s orbital. S orbitals being that beach ball, solid, that sphere of where the electron can be. Second energy level has s orbitals, but it also has p orbitals. Has 3 p orbitals, and each orbital can hold 2 electrons each, so it has a total of 6. Okay. Third energy level, we're going to build more orbitals, more shells, if you will. It has an s orbital, it has a p orbital, and it has a d orbital. D has 5 different orbitals within it, and each one of those can hold 2, so a total of 10 electrons. The fourth energy level adds the f orbitals. 7 orbitals, each can carry 2 for a total of 14. Okay. Fifth, we're not going to go any higher than the f orbital, by the way, but we do need to have this for the diagram just so you can see the concept. And so on. So how many electrons are in the first energy level, potentially? 2. So total, this holds 2. The second energy level, 8. And if we were to add them up, so this is, I'm going to just put cumulative there, just as a way of saying, okay, there's 2 total in that energy level, but how many can we hold up to that point? Well, 2 plus 8 is 10, plus 18 is 28, plus 32 is 60. Okay? So once we get to 4F14, we have accounted for up to 60 electrons. Up to 60 electrons, going over here, we have made it all the way down here in our periodic table. I mean, we've covered all the way down to this point here, and we've come down into the lanthoid series, the F block here. So that's just one way to consider all the different energy levels. And again, the first number here is the energy level that relates to the rho, and the second number is the number of electrons in those orbitals. So there's a slight wrinkle. And to go into why this is, again, is kind of beyond the scope of the course. So I'm going to ask you just to, it's a frustrating consequence, but we need to just acknowledge it and deal with it, is that, as I said before, that the electrons are going to fill from the lowest energy level and fill outward. And though it generally follows that the first, second, and third, and as you go higher here, it's a higher energy level, and as you move to the different orbitals, it's a higher energy level. But the electrons don't technically always fill in that nice, neat order. There's a little hiccup to this that you need to understand. And we understand this hiccup by drawing what's called these slant diagrams here, or the slant arrow. If I do this, it helps me understand how the order of the electrons fill. So what we're going to do is look across here and say, okay, if I understand the concept that I'm going to fill in the order of the slant arrows, I can draw my diagram initially by going first, second, third, fourth, fifth, and in the first through fourth I add an energy, or add an orbital, an s, a p, a d, and an f. Okay? Now I say, okay, if I have to account for a lot of electrons, let's just start building up electron configuration. Mr. Baker said they're going to start at the lowest energy level, number 1, and the lowest orbital, s. And the lowest position within that orbital, 1, and then 2. Well, then I'm full. Then I need to go to the next one. Let's start building up an electron configuration. See over here that I have a 1s2. When I have a 1s2, I'm saying I've got 2 electrons in the first energy level in the s orbital, 1s2. Next, following the slants, 2s2. And then 2p6. Then 3s2. And then 3p6. And then 4s2. Now, up to this point, nothing surprising has happened. They filled in order. First energy level, all of its available orbitals. Second energy level, both of its available orbitals. Third energy level, 2 of its energy levels. See that? Doesn't the third energy level have a d shell, or d orbitals? It does, but the electrons don't fill the d first. They fill the 4s first. Again, why is outside the scope. I just need you to go with this. So by using the slant diagram, I see that in the third energy level, 3p6, then 4s2, guess what starts getting filled next? The 3d10. After the 3d10, the 4p6, and then the 5s2. This is a way of determining what your electron configuration looks like for the element if you don't have a periodic table available to you. And again, a lot of times you're asked, come up with the electron configuration for, let's say, rubidium. Okay? Without a periodic table, if you just knew that the atomic number was 37, you would say, okay, 37 protons, neutral atom, I've got 37 electrons. Okay, I need to account for 37 electrons total. Let me do the count. If I drew it out like this, I'd go 2, 4, 10, 12, 18, 20, 36. I only need one more, so that'd be 5s1. So I'd have all of this, and instead of 5s2, rubidium would just be 5s1. There, I've accounted for 37 electrons, and they fill in that order. There's my 37. If it was just 30, or excuse me, 36, I just lose one. There's my electron configuration for 36. For 35, I need to lose another one, right? So I'm just going to be down to... So counting up how many electrons you need to account for by looking at the configuration. Now this is using the slant diagram. This is filling in this order, and again, it's the same as if you filled across 2s2, 2p6, 3s2, 3p6 until you get to the 3d10. 3d10 is kind of out of order because you're going to fill 4s2, then come back and fill the 3d10. Now, a much easier way of figuring this out, and it's one that I've already used with you, you've already become familiar with, is looking at the periodic table and recognizing that the shape of the periodic table is shaped based upon this electron configuration. Before, when the biggest thing we had to be concerned about was, whether or not we had a metal or a non-metal, that was the most important thing in our world. But now, a much more significant thing in the world is valence electrons, and how does that describe what a metal actually is? How the electrons are held around the nucleus, and that's what this chart is designed to portray in a very simple way. And again, because we've been using it, this is not new to you, but maybe in application, it'll make a little more sense. Okay? So looking at the same number here, let's say that we were back at 37, so we had 4p6, 5s1 was rubidium 37. Okay? I can figure that out by counting 37 electrons using the slant diagram and coming up with this sequence. I can also look at the periodic table and see the same information pretty quickly and visually. Okay? The 1s shell we said before is row 1, the s1 and the s2. So 1s2 gets me to helium. Then I move down, second energy level, the s block. So this is 2s1 and 2s2. As I read straight across, I then go to 2p, 1, 2, 3, 4, 5, and 6. Right here, 2p, 1 through 6. So we've accounted for those three just by looking at it graphically, visually there on the table. Then we come over, after we get to neon, we come back again to sodium. We're now at the third energy level, right there. The first thing we fill is the s. We have two of them. And as we read across, there's nothing in the middle. There's no D block. Right over to the F, and we have 6 more. That takes us all the way over to argon. From argon, come back around now. We're at potassium, the fourth energy level. We fill the S block, S1 and S2. It's right there. Then, now we suddenly have something graphically that's in our way. See that? Right in here, the D block. But what do you notice that doesn't seem to make sense from the D block over here and the D block here? What seems to be out of order? Looking at it graphically, you would expect this to be the 4D, the 4D10. So as you're using the periodic table, they did keep them in order of atomic number, but in terms of your energy level, when you get into the D block section, you have to subtract 1 from the energy level. What do I mean by that? Well, this would appear to be 4s1, 4s2, and you would expect this to be 4d1. But because of the way they fill, this is actually 3d1. You take the energy level here, which is 4, and subtract 1 from it. So again, this would be 3s1, 3s2, 3p, 1 through 6, 4s1, 4s2, 3d1. Subtracting 1. So over here, if we look at, I don't even know what the Y, I don't remember the name of it, but I can tell right now that its valence shell electron, its electron that's farthest away from the nucleus, is in the 4d1 position. It's in the 5th row, but every one of these subtract 1 from the energy level to make it 3d10, over here, as we went through, this would now be the 3d10. What's next? We go back to our true energy level of 4 and the 4p block. So 4p, 1 through 6, takes us all the way over to krypton. It brings us over here to rubidium, 5s1. Okay, so I've accounted for all the electrons using a slant diagram, counting them out, 2, 4, 10, 12, 18, 28, 30, or using the table by flowing across to the 1, 2, 3, 4, remembering to subtract 1 from the energy level when we fill the D block. Yes, Ike? Mm-hmm. You can tell that whatever this is, if its final orbital is the 5s1, it's got to be rubidium. If all of this is right, this has to be this, because it fills the 5s1 position as its valence electron. Okay. Now, a shortcut for this, okay, really easy, is we just said, Ike just brought to our attention that this 5s1, it has to be rubidium because its valence electron is in the 5s1 position. There's a shorthand way of writing it. This orbital is not full, right? But there's a shorthand. We go back to our column 8. These are called the noble gases. Okay? Another way that I can write all of this here is to shorthand it by doing this. (5s1). What this is telling me is whatever my electron configuration for this element is, and it has to be the preceding. So if I'm looking at any element, if I go all the way to the right and go up 1, the preceding noble gas plus what? If it's rubidium, it's going to be S1. Strontium is going to be S2. Okay? So this would be a full electron configuration. This would be the abbreviated electron configuration. Okay? All right.